好，那我最先要说的是，就是你如果是旁听的哦，还是在网络上的，你要给我你的名字跟 email，要不然的话，我不能把你放进那个 pool 的 course website。course website 上面有很多资料譬如说，我们的课本2本书都在那里，而且我每一次讲课以后，我会把讲义放在库里面，还有一些其他关于那个我们这一门课的消息，我都放在那里。譬如说，那个我们的考试还是没有考试哈，习题是每2个礼拜什么时候要交，要怎么交习题等等都在那里。那个今天我会把第一个功课放在库的那个 course website 上面那个你们有2个礼拜可以做功课那你们是可以那个互相讨论的不过你写一定要自己写，不可以抄别人的那个你如果跟那个别人合作，你要把你的同伴的名字写在上面Okay. Okay. So are there any questions? Yeah. So just to remind you before you go, if you're an auditor, put your name and email address here. And if you are online, then you send me your name and email address so that I can put you in the course website. Okay. Now, this course is being filmed. And one of the disadvantages of being filmed is that if I make a mistake, it's there forever for posterity to see. So last time I made a little mistake and I want to correct it. And that is the German word for cycle. So, yeah. Cycle in German is actually spelled Zyklus, okay? I spelled it wrong last time, so let me make that correction. Okay, now, a differential form that's a cycle is called closed, okay? So a K form, omega is closed if the omega is 0. And then a differential form that's a boundary is called exact, okay? And so omega is exact if it is v of some other form. So omega is equal to v tau for some tau of degree 1 less. Okay. All right, so last time I defined the theorem cohomology of an open set in Rn. And today I want to define another cohomology. It's called cohomology with compact support. Okay, so let's first define what support is. Okay? Now, suppose you have a function that looks like this on some open set U in R. Then let's say this is 0, and here it's 2. Okay, so F from the picture, you see that F is not 0 on the open set 0, 2. The support of F is the closure of the set where it's not 0. So the support of F is its closure, the closed interval 0, 2. Right? Okay. So that's a definition of support. Also for a form. Now, let me see. Okay, so let's make this definition. Okay, first, the 0 set of a K form on U. U is always an open subset of Rn. Is, let's call the K form omega. So Z of omega is the set of all points in U such that omega at P is 0. Okay, that means it's the identically 0 tensor at each point. And then the support of omega is, okay, it's the closure of the set where it's not 0, so it's the complement, the closure of U minus the 0 set. And here, you know, U is an open subset of Rn. You can take the closure in U or in Rn, but it has to be the closure in U, okay, in the domain. Okay, this is not D, it's the closure. So that's a definition of the closure. It's a closed set. And then I also use the notation Z of omega C for the complement. Okay? All right, and so now we can consider not all smooth forms, but smooth forms with compact support, and that will be omega sub C, okay, Ku. That's the C infinity K forms with compact support in U. And what we would like is a differential complex, okay, of forms with compact support. So you have to know that if you have a form with compact support, then D of it also has compact support. And so that's what I want to show. Now, the first proposition is that D, the exterior derivative, decreases the support. Okay? So D is support decreasing. And what that means is that if you have any form, omega, any form on U, then the support of d omega is a subset of the support of omega. Okay? Yeah. All right. Now, so let's prove this. I have to cover that up a little bit. Yeah. Okay. Okay. All right. So I think I better write down what we want to prove here so that we don't forget. Now, it turns out that it's easier to prove the complement, you know. So we prove instead, let's take the complement of both sides. Support of omega C is contained in the support of d omega C. Okay? So here's a picture. So suppose this is the support of omega, and you have a point P that is not in the support of omega. Okay? So it's out here. Okay, now, because the support is a closed set, and you have a point not in a closed set, yeah, so the complement is open. So what does that mean? Tell me what that means. You have a point in an open set. What does that mean? If you have a point in the open set, yeah, then, yes, somebody back there? Yeah. That's right, yeah. If P is in this open complement, then there's a neighborhood, V, okay? That's in the complement. Now, if it's in the complement, then omega is entirely zero here, right? Because this is where it's non-zero. It could be zero on the boundary too, but it's definitely zero outside the support. Okay? So since the support, by definition, is closed, and P is in the complement, there exists a neighborhood. A neighborhood is always open, right? V of P such that V is contained in the complement. Okay? And so that means, because if it's in the complement, that means omega is identically zero on V. Now, if you take the exterior derivative, you know, that's just given by partial derivatives. So if omega is 0 on an open set, then all the partial derivatives of the coefficients are 0 there, and therefore d omega is also 0. Hence, d omega is entirely 0 on V. And what does that mean? D omega is entirely 0 on V. So, yeah, yeah. So like, so that means P, you know, like you have the support of D omega. That's where it's not 0, and you have some open set. It might intersect the boundary around P. Okay. It's entirely 0, so it cannot be here where D omega is not 0, and so you know that that's D omega at P is not in the support. Sorry, P, yeah. So P cannot be in the support of D omega, right? If it's in the support of D omega, then it's either in here, then it's not 0, or it could be here, then every neighborhood will contain some point where it's not 0, but we know that P is out here, you know. You have a neighborhood that on which D omega is 0. So P has to be outside the support, and so P is in the complement of the support. Okay? So I have proven this. If I have a P here, then it's here. Okay? Yeah, so that proves the proposition, okay? The proposition here that D is support decreasing. Okay? And so now I want to prove that D will take a form with compact support to a form with compact support. Let me see, what's the best way to do that? I think it's to move this up and to move this down. Okay, yeah. So, okay. You know, I think I'm gonna do this. Just write on half of the blackboard so that I don't have to move the blackboard up and down so much. So let's prove the theorem. Well, actually, it's so easy. It's a corollary. So if omega has compact support, so does d omega. Okay? And why? Because we know that the support of d omega is a subset of the support of omega. Okay? And the support of omega is assumed to be compact. And we know that the support is always closed. Okay, there's a theorem in point set topology that says a closed subset of a compact set is compact. So it's that easy. Yeah, yeah. I'll just say, yeah, so support of d omega is compact. Okay. Okay, and now I think I have to move it up so that it's easier to write. Yeah, so, okay, so this means that, you know, D will take zero formed with compact support to one forms with compact support to two forms with compact support. Okay? And you start with 0, and you end with omega n, because you cannot have a non-zero form of degree more than the dimension of the set, right? Yeah, so we have this. This is a sequence of vector spaces such that d squared is 0. That's called a differential complex. Okay? A differential complex just means it's a sequence of vector spaces such that d squared is 0. A sequence of vector spaces and linear maps D with d squared equal to 0. Okay? You have a differential complex. And whenever you have a differential complex, you can define its cohomology, okay? Like before. And so we can define cohomology with compact support. Oh, God. I have to go to the gym more often. Okay, so we define HK with compact support of U, you know, to be ZK with compact support of U over BK with compact support of U. Mm-hmm. So ZK with compact support, that's just the closed K forms with compact support. And then BK would be exact K forms with compact support. And so that's the cohomology with compact support. Now we should do an example. Yeah, but yeah, before we do an example, I want to talk about degree 0, okay? Because I didn't talk about it last time. Okay, now a K form is a K tensor at each point, an alternating K tensor at each point, okay? And a K tensor has K arguments, okay? K independent variables. What is a zero tensor? A zero tensor, it is a linear function on the vector space with no argument, no variables, okay? So a zero tensor is a linear function on V, the vector space, with no argument, no variable. What is a function with no variable? It's a function that doesn't vary. So it is a constant, okay? Yeah, so we should define a zero tensor to be a constant. Yeah. Okay, yeah. Yeah, we might as well just make that into a definition. A zero tensor is a constant. Okay, yeah. Zero tensor on a vector space V is a constant. Okay? It's just a number. And because there are no arguments, there's nothing to alternate. So the alternating zero tensors are also just constant. So A0V is just R. Okay? And then what is a zero form? A form assigns to each point a tensor. A zero form assigns to each point a number. What is that? A function, yeah. Okay. So a zero tensor is a constant and a zero form is a function. And that means C infinity zero forms are just C infinity functions. Okay, so thus, omega zero of U, okay, that's the C infinity zero forms on U, and that should just be C infinity functions on U. So that should be C infinity functions on U, all right? Okay, so let's calculate an example. Let's calculate the cohomology with compact support of the real line. Okay? And let's start with degree 0. Yeah, so you have to look at, omega 0 with compact support to omega 1 with compact support. That goes to 0. And now we know that this is just the C infinity functions on U, but with compact support. And so what are the closed zero forms? So the closed zero forms with compact support, that's C infinity function with compact support such that df is 0. df is f prime x dx, and you want that to be 0. And that just means that f prime is 0, okay? So f prime is 0. If f prime is 0, f is a constant function. on R. Oh, sorry, this should be R. Thank you very much. Yeah. Yes, like if I make a typo on the blackboard, you have to correct me because as you know, it's film. So we don't want mistakes to be there forever. And here too. Yeah. Uh-huh. You know, this doesn't mean that I'm senile. Yeah. Because when I was young, I used to do this all the time too. Yeah. It's just me. Well, a constant function on R, does it have compact support? Yeah, only if it's zero, right? So, yeah. So for F to have compact support, F has to be zero, okay? And that means the closed zero form with compact support is zero. And so H1 with compact support, that's Z0C over B0C. That's 0 over 0. Well, you know, this doesn't mean that you're dividing 0 by 0. This means you're taking the quotient space of 0 by itself, and so you get 0. You get the 0 vector space, okay? Yeah. Oh, no, this is H0. Yeah, H0. Okay, so H0 is 0. And now let's do H1. So I will push this one down. Ooh. Okay. Yeah. Okay, so for H1, you have to look at Z1C. Okay. So that is one forms. One form looks like this, Gx dx, such that G has compact support. And Vg is 0. But DG is a two form. A two form on R is 0. So this is automatic. Okay? Yeah, so basically it's just a function with compact support times dx. Okay? And then what is B1C? It would be df, right? So df, that's going to be f prime x dx such that f is a function with compact support. Okay. And now the question is, well, now is every G F prime? Is every function with compact support the derivative of another function with compact support? And the answer is no. And it's because, it's because if you have a derivative with compact support, okay, so F has compact support. And this is, sorry, I mean, we are doing R. Okay, so this is R. If it has compact support, then it's contained in some, the support is contained in some closed interval, AB. So F is going to be 0 towards minus infinity and towards plus infinity. Okay. And so like if G of X, if it's a derivative, then the integral of G of X dx from minus infinity to infinity is the integral of F prime X dx from minus infinity to infinity. And the integral of the derivative is the function which you evaluate from minus infinity to infinity. But because F has compact support, at minus infinity, that just means a very big negative number, it's 0. And at plus infinity, it's also 0. So this will be 0 minus 0 equals 0, since F has compact support. So you see that not every function with compact support can be the derivative. It has to satisfy this condition that its integral is 0. Okay? Now let's look at this map, the integration map. Okay. So let's look at this integration map. From minus infinity to infinity, okay, that goes from Z1 with compact support to R. Okay. So what we have proven is that if you start with an exact form, then the integral is 0. So we have proven that the exact forms with compact support is in the kernel of integration. Okay? And I want to show that the reverse is also true. Okay? So if the integral is 0, then it's exact. Okay? So suppose the integral of G of X dx from minus infinity to infinity is 0. I want to find this F. Find F of X such that G of X is the derivative. And how would you define this F? It has to be, right? Yeah, it has to be the integral of G. So we define f of x to be the integral of G of u du. And where should you start? You might as well start at infinity. Okay? You know, because I mean, G has compact support. Yeah. So it's going to be 0 out there at infinity. So we define it to be this from here. Okay? Then by the fundamental theorem of calculus, G prime is F. But what do you have to check? Are we done? Yeah, you have to check that F has compact support, okay? So let's check that F has compact support. Yeah. Let me see. So now, so I know that G has compact support. Okay, so G looks like this. Maybe I get to use a different color, but not green. How about this blue? So maybe G looks like this. Okay, it's got compact support, you know, so it's 0 outside this interval AB. And we are integrating G from minus infinity. Okay, so f of x is the integral from minus infinity to x of G. So you see that if x is less than a, then there's nothing. When you integrate up to a, you get nothing. So if you assume that the support of G is inside this interval, then f of x is 0 for x less than a. And oh yeah, and then like if x is greater than b, then basically you are integrating over the whole real line because there's nothing beyond b, right? There's no area beyond b. And so for x greater than b, you know, the integral from minus infinity to x of G of u du is the integral from minus infinity to infinity of G of u du. And that is by hypothesis, it's 0, okay? We are assuming that G is in the kernel of integration by hypothesis. Okay? And therefore, yeah, so f yeah, f is 0 for x less than a and for x greater than b. And so the support of f is contained in the interval AB. And so it has compact support. Yes. Okay, so what we have proven is that, yeah, G of x dx is f prime of x dx for f with compact support. And that means g of x dx is exact. This is df. Say, this implies that g of x dx is in the boundary with compact support. And so we now have the other direction. And so we have proven that the kernel of integration is precisely the exact forms. Okay, yeah. So and now, so we've got this map integration, and obviously it's surjective, right? Because you know, you just pick some G that has a non-zero area, then the integral is non-zero. And then if you take multiples, it'll give you all of R. So this map is surjective. I would just say it's obvious because I don't want to write it down to prove, okay? And has kernel equal to the exact form. Okay, now there's a first theorem, structure theorem in linear algebra, or the, oh yeah, no, it's called the first isomorphism in linear algebra, you know, that says, yeah, what does it say? by the first isomorphism theorem of linear algebra, it says, if you have a map, then the domain over the kernel is isomorphic to the image. Okay, so the image is R. Domain over the kernel. I wish I had some space here. Okay. I guess I have to write sideways. It's just Z1C over B1C, and that's H1C. Okay? Yeah. So now we have computed the first cohomology, and it's R. And the zeroth cohomology is 0. It's just the opposite of ordinary de Rham cohomology, right? All right, let's stop here and we come back again at 11:20. So for those students who are online, I said you have to write me with your name and email address, but I didn't give you my email address. So here's my email address. Okay, yeah. So this is where you write. And all of you can also write me at this email address. Okay. So, yeah, we have shown that the cohomology of R looks like this. It's R, in degree 0 and 0 in degree 1. And then for compact support, it is 0 in degree 0 and R in degree 1. Okay. So you notice that they are upside down. And this is often true, okay, in general, that the cohomology with compact support is the cohomology without any restriction, but turned upside down, okay? And that's called Poincare duality. And the condition on the manifold is that it should be what's called orientable. And that's what we would like to show. Okay? Not just for open subsets of R, but in general, for any manifold. Okay? So for the rest of today, I want to extend everything that we have done so far to manifolds. And manifolds, you can think of as just higher dimensional surfaces. I will give a technical definition, but it's really not that important. We don't really use a lot of properties of manifolds. Whatever we use, we can just assume. So let me begin with the definition of manifolds. I think most of you have probably studied this already, but just think of this as a review. So a manifold is basically a generalization of a smooth surface. And the most important property is that every point P locally looks like Rn. So there is a homeomorphism to Rn, to an open subset of Rn. Okay, so this is Rn. And this U is homeomorphic to its image. Okay, and then if you have another open set, that's also homeomorphic, to a different open set of Rn, this is Rn. Then it's like having two coordinate systems, on the intersection, okay? Because an open set that's homeomorphic to Rn, it really just gives you coordinates, okay, on the open set. And so these two homeomorphisms give you two different coordinate systems. Since this is a homeomorphism, you can take its inverse, and the inverse is just a parametrization, of your surface by points in Rn. When you have two coordinate systems, you want the two coordinate systems to be related by C infinity map, okay? Because we are only, looking at C infinity maps. So the requirement is that when you go this way, from one coordinate system to the other, and that's 5 composed with side inverse, this should be C infinity. And if you go the other way, it should also be C infinity. So the other way is side composed with phi inverse. That should also be C infinity. Okay? So, yeah, so let me write this down. Phi should be a homeomorphism, and psi is also a homeomorphism from their respective open sets. Oh God, this should be V. Okay, and then you put like 2 additional conditions on your topological space, and that is, it should be Hausdorff and second countable. Okay, so what does Hausdorff mean? Let me see. Can somebody tell me what Hausdorff means? Yes. Yeah. So Hausdorff means that you can separate points with open sets. Okay. So what that tells you is that you must have enough open set to separate points. Okay. So it says the topology cannot be too small. Okay. What does second countable mean? Second countable. Okay, good. Yeah. So it means that you have a countable basis. Okay? And a basis you can think of as a collection of open sets such that every open set is a union of these basic open sets. Okay. But you must have a basis that's countable. Now, countable means it's not too many. Okay. It's not as many as points in the real line. So second countable means that the topology is not too big because you must have a countable basis. Hausdorff means that the topology is not too small because you have to have enough open set to separate points. And therefore, the two conditions together say that your topology is not too big and not too small. Okay? So it's very reasonable. All right, so let me write down the definition of a manifold. But I don't want to write everything down because that would be too much, you know? And anyway, you can look it up in the book. So a topological manifold is a locally Euclidean Hausdorff and second countable topological space. Okay? Locally Euclidean means this. Every point has a neighborhood that is homeomorphic to an open subset of Rn. And then, so locally Euclidean means for all P in M, there exists a neighborhood U and a homeomorphism phi from U to phi of U in Rn. And this is called a chart. U together with this homeomorphism. And two charts. So charts U phi and V psi are C infinity compatible if the transition function, okay, from the image of the intersection to the other image of the intersection, and then the other way around, are C infinity maps of open subsets of Rn. And then, so an atlas is a collection of charts a collection of C infinity compatible charts. That cover M. Okay? And then a C infinity manifold is just a topological manifold with a maximal atlas. Okay, let's write that down. So a C infinity manifold, we also call it a smooth manifold, is a topological manifold M, okay, together with a maximal C infinity, a maximal atlas. Well, maximal just means that it's not contained in another atlas that's bigger. Right? Okay, so that's the C3 manifold. And then we have to define what, oops, oh gosh. Now we have to define the tangent space. Okay. So to define the tangent space, I first define the partial derivative. Okay, you see, now we have this homeomorphism, okay? And then R1 and R2, they are coordinates on Rn. Okay? So they're really maps on Rn. You can compose them, and that's what we call xi. So let R1 to Rn be the standard coordinates on Rn, and xi is Ri composed with phi. So xi are now coordinates on U. And so U with this homeomorphism phi, can also be written as U. And then the map phi, it has n components, x1 to xn. Okay? So x1 to xn are your local coordinates on U. And if you have coordinates, you should be able to differentiate with respect to them. Oh gosh, I shouldn't have erased this, but it's okay. Let's just, so I want to define, okay? Let's say f is a function on U. So I want to define df dxi, okay, at a point P in U, and I have this map phi. Okay, so I want to define the partial. Okay, so the way you define it is you always pull it back to Rn. Okay, so you have the inverse map of phi inverse. Then if you compose f with phi inverse, you have a function on Rn that you can differentiate. So you compose with phi inverse, and then you differentiate with respect to the coordinate in Rn. Okay? And you evaluate it at the point phi of P. Okay? That's the definition of the partial derivative. And this I can also write as ddxi at P, okay, applied to F. And, okay, so, the unit vector in this direction is ddri. Yeah, and that's what we call a tangent vector in Rn. So ddxi at P, that will be what we call a tangent vector of the manifold at P, okay? And so let me define the tangent space. Okay? Now, this is not how people usually define the tangent space, but this is a cheap way to define the tangent space because it's very quick, you know. You know, in my book on manifolds, I define a tangent space as a derivation at a point P, you know, but I don't want to get into that here because that would take too long. So, definition. Okay, the tangent space at P of a manifold M, okay, is just the vector space spanned by ddx1 at P to ddxn at P. Okay? And you're going to say, oh, well, what if you use a different coordinate system? Okay, then you would have ddy I at P, but it's okay. You can show that they span the same tangent space, okay? Because you can write ddyi in terms of ddxi and vice versa. Okay, so now once you have the tangent space, then everything is exactly the same as before. So what would be a K form on a manifold? Can somebody give me the definition of a K form on a manifold? A K form on an open subset U is an assignment to each point in U of an alternating K tensor on the tangent space. Okay, okay. Now just repeat that after me. A K form on a manifold, come on, is an assignment to each point P of the manifold, an alternating K tensor on the tangent space at P. Okay? So yeah, it's exactly the same as before, okay? And then a K form will be a linear combination of the, oh yeah, so then you have the differential, you know, of a function defined the same way as before. So you know what dxi means. And then you can write a K form in terms of the wedge product of the dxi's, and a K form is C infinity, you know, if the coefficients are C infinity. So everything is exactly the same as before. So we don't need to write that down. And so now we can define the Ram cohomology on a manifold, okay? We still have the same exterior derivative and everything. And yeah, so we define as before everything. Every, yeah. And then we end up with the cohomology of M and the cohomology with the compact support of M. Okay? So next time, we will start computing cohomology of manifolds. Okay? So we'll develop techniques so that we can compute the cohomology, you know, of a circle, of a sphere, of a torus, anything. that you can think of. But the thing is like, yeah, you can compute things that you can visualize using elementary techniques. But if you want to compute, say, the cohomology of the orthogonal group, then you need more advanced techniques. And that's what the whole course is about. We're going to develop techniques to compute de Rham cohomology and cohomology with compact support and study their properties, like Poincare duality, so when does it happen that the cohomology with compact support, it's just ordinary cohomology, but upside down, and like, how do you compute the cohomology of a Cartesian product, things like that. Yeah. All right. So we'll end here today. And today I have time. I don't have a lunch appointment, so you are welcome to come talk to me after class if you like. All right.